Hello, hello. Hello, oh, hello, 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 Eugen. Thank you. Hello. It's so nice to see you. Hello, well, everybody, but specifically, hello, Eugen. Hello, Kayla. Hello, Kayla. Good afternoon, Sylvie. Good afternoon, Ariana. Hello, Isabella. Hello, Marina. Hello, Ashley. Hello, Devin. Good afternoon, Sulady. Hello, Jonathan. I appreciate it. Who else? And Ariana. Or did I say Ariana? And Jake. And Ashley. Okay. Anyway, enough hello. So first of all, let me say hello to the elephant in the room, the Kaparaja in the room. So you probably saw in the Google Classroom, some of you have gotten your exams back, but most of you have not. And the order in which they're coming back is random. And when I say some of you, I don't even just mean some in this class. I mean in all the 4 classes of mine that all took exams on the same day, stupidly, my stupidity. So this is a total apology. I just want to make it clear that first of all, if you haven't gotten your exam back, that is just mean you are going to, and it means the machine is now in progress and they're coming back, and you will get it soon now. Like finally, like the ice got broken and they're starting to come back, but they're coming back one at a time. And if you happen to have gotten yours back, that's great, and I'm happy. And if you haven't yet, it reflects nothing on you. It's random. It doesn't mean anything that you other than that I'm slow. And you will be getting it soon, certainly before we meet again. That's number one. And I totally apologize, and I know it's very anxiety provoking and very frustrating not to have your grades or your work back yet. I don't want to spend 2 hours talking about it, obviously, but I just want to acknowledge, like, there's no excuse for it. I mean, obviously, I've run into certain jams, and some of you who often look for me on Tuesdays, or I look for you on Tuesdays, I canceled my classes on Monday, and I wasn't in school yesterday for reasons that are not private, but are not worth going into in the middle of class. But I'm happy to talk about it with anybody directly. But so I've obviously fallen very behind, and none of that is an excuse. If I were in your position, I would definitely have wanted my exams back already. I will get them I'm getting them now, and they will come very soon. But I just want to acknowledge also, as I tried to indicate in the classroom, you will not be punished for this frustration. I mean, this has happened to me before, and I know how frustrating it is to you. So let's be clear about a couple of things. First of all, there definitely is no more work that you have to do unless you still owe me old stuff until the final exam. Also, let's be clear. I know you can't even think about a final exam or prepare for it until you get back these results. I know that. The final exam will be shorter than this exam was anyway. There's very little time left in the semester. I know that. So you all have done your job and you've gotten yourself over the hump. The main thing was getting past the midterm. The final exam will be shorter, will be less material. And let me make this clear too. I mean, this has happened to me in the past, and let me just make it clear, but you haven't had me in the past. So let me make it clear. Since there won't be a huge amount of time between you getting back these results and the final, I know that can put you in a that could put things in a jittery state. So first, let me say this. Most of you will still turn out to have done well on the midterm. I believe you will. Like, you can't know that until you see it, but I believe you will. It looks like that so far. If you end up getting a fine score on the midterm, a score that you're satisfied with, or that looks like you're doing well in the class, then you're not going to have to reinvent the wheel on the final. I do have to count both tests. I can't discard one because we only have 2, but I will tell you right now, something I've done in the past is I'm going to, whichever of the 2 tests you do better. Wait, let me just let this person in. And I'm going to ask you in a minute if this is clear. Hold on. I know I just lost the board. Okay. And obviously this is recorded also, but it'll turn out that whichever of the 2 exams you do better on will count more in your average than the other. They will both count, but I will more heavily weight the one that you do better on. Therefore, well, the point of that is, like, and again, that's an acknowledgement of the fact that it puts you in a jittery position to not know what's going on, you know, for a long time period before the final. So when you find out, if it turns out you did well here, just know that you can put a little less stress and less concern into your final, that your final will not destroy the good average that you've developed in the midterm. If it turns out that the midterm was rocky for any of you, or for one of you, or two, whatever, then you'll have a chance. Then the point of the final for you will be to help you out and give you a chance to do better. So whichever one you do better at will count more. That's not a million times more, but more. Number two, and again, I'm just saying all this to get out of the way because I know I just want to make it clear. Physics is hard enough without it being made harder by my inefficiencies. So, and I can't do anything to undo some of my inefficiencies, but I can make it clear that they are recognized and they are built into the system of compassion for you. So the other thing is that, and I'm going to make the speech again, like in the last class or two, I always do make the speech, but you know, your final will also be run the same way. It'll be like take home and all of that. You'll have a pretty good sense by then of what's happening with your grade, and most people will be doing fine in the class. But just so you know, and I really shouldn't say this in public, but it's true. Nobody, what will not have it. If I feel like there's an issue, if I'm grading this exam, or, you know, if I turn back this exam and I really think that you're in jeopardy in the course, and by jeopardy, I mean like a D or an F, I will reach out to you. That's number one. I won't necessarily reach out if you're in the C range, although I think most people will not be in the C range. But if you, once you get this exam back, if you think you might potentially be in the C range in the course, definitely reach out to me and we'll see if that's the case or not. Getting a 75 on this midterm, I don't want to overtalk numbers because you don't have them yet, but even getting a 75 on the midterm does not mean that you're getting a C in the class, because there's lab and there's all these other things. But whatever, if you have a concern, you'll reach to me. If I have a concern, I'll reach to you. What I need you to know is the one thing that will not happen to anybody, and this is a promise, what will not happen is you will not find out from CUNY first for the first time when everything is over. You will not suddenly see a D or an F on CUNY first without having ample warning and knowledge of something to do to rectify that situation. I just want to make that clear now, because I know we're in the stage where people are worried about like what's going on with my grade. In fact, and some people have asked me, if I think that you're heading for a D or an F or anything in that range, I will be letting you know, and we'll be talking, and there's a chance to do something about it, such as on the final. If in the worst case scenario, if we get through this midterm, and then you get to the final, and I don't want to overtalk this, but I want to make it clear because I'd want to know as a student, if in the worst of all scenarios, if heaven forbid, you take the midterm, you get it back really late, and you didn't realize that you thought you understood the material, but you didn't. And then you get this midterm back so late that it turns out you don't understand the material. Now you have very little time to prepare for the final. You prepare for the final, but you don't but whatever, there wasn't enough time. And then you have a real struggle with the final. If in heaven forbid, if all that happens and I'm going home the night before grades are due and I'm grading the final, and I find out for the first time, oh my God, this person, whatever, Ron, is going to fail this course or get a D. And I totally did not see that coming, and they didn't see it coming, and I never warned them, and there was no chance for them to do anything about it. And all of a sudden there's going to be a D now. It's not going to be a D on CUNY first. I would not do that to a person. You can't find out for the first time when it's too late to do anything about it that you're not passing a course. So in the worst case, and this happens like every semester, if all of a sudden, because maybe the final went completely awry for whatever reason, if it looks like you're about to get a D or an F in the course, what's going to happen is you're going to get an incomplete. And I'm telling you right now, if you see incomplete on the transcript, what that is a signal from me to you to say, reach out to me. Something is incomplete in either my understanding of your situation or your understanding of this course. Like there's something we did not communicate completely enough to bring this to resolution. So you reach out to me and we will find a way to either redo something on the final or do something. And that's not what incompletes are supposed to be for. I shouldn't be saying this like to the universe, but it is the way I use them. I use incompletes to mean there is something incomplete between you and me, and it might be my fault and it might be your fault, but let's try to rectify it before a D or an F lands without any warning. So if that's in the worst case scenario, you will not, you will get a chance to rectify a situation if all of a sudden it looks like we're at that point. Okay, that's in the worst case scenario. If you think you're in C land, then reach out to me and we'll see. But I'm saying all of this again to say, I know it's super annoying not to have your midterm grades yet or your midterm knowledge, and they will be coming soon. But just know that I know that, and my knowledge is built into the system. The goal is still for everybody to do as well as possible. Everybody who tries, who does anything. Okay, I hope that, so now I'm going to look at, so I know I'm just yammering, but I want to get back to the material. Obviously, I don't want to spend 2.5 hours on this, but I want to acknowledge that. So hold on, let me just look in the chat and then put the book. Oh yeah. Good question. Sorry. Wait. Okay. Good afternoon. Yeah. Sylvie's question. Yeah. The final review. The final will work just like. It'll be shorter, but same deal. You'll get a review, and maybe you'll even go over it in lab with Mercedes or whatever. And yes, you'll get a practice. You'll know what's on the final before you get it, and you'll take it home and do it during finals period. I can't tell you right now exactly what it's going to be due, but all the same routine and the same. Yes. To Sylvie's question, yes. And hello, Nicole. Okay. Okay. Oh, thank you, direct chat person. Okay. I appreciate and also you all no, I appreciate someone just said something nice in the chat. That's cool. I appreciate it. But if you're still pissed off, I'm not trying to I understand. Just reach out to me privately and I will hear you out. I know this is not ideal, but okay. That said, wait, why are people black and white? Okay. That said, and I know we have a long class too. So if you start, if we in the middle, if something comes up, let me know. But now I want to go back. What I want to do is you've had now we did this whole big thing on Doppler effect last week. That was intense. That was a lot. Usually that whole business does appear as one of the big problems on the final. And we link it back to the universe and all this. So that was a lot, and we'll revisit it in a review or whatever, like Sylvie was asking. But I'm gonna leave that aside for right now. And now try to re-hook up with what's been the seemingly new topic that's been going on now for 2 weeks in your lab. My understanding, so we're gonna talk again. My understanding is that you had this seemingly out of nowhere circuit lab 1 week. You had a bunch of true false motions regarding it. Then if I understand correctly, since it was whoosh, out of left field, people were not totally confident with what was going on and found the true false motions challenging, I believe, or didn't feel like they were in a position that they could do it. So then in my understanding, 2 days ago, I think you sort of reinvestigated similar operations, similar procedures, similar data collection, but got a different set of true false questions to investigate in the hope that maybe a new perspective on the same thing might help to gel things together. First of all, is that understand? Yeah, that's a yes, Jake. Okay. So good. And I'm here now finally to try to, we're going to try to bring this all together, but that's good if I'm not crazy, at least in that respect. So let me ask, so I want to try to address it frontal, in terms of exactly what you were asked. So let me ask the true false, I guess it turned into a board meeting, I guess. The true false questions that you got just 2 days ago that you turned into a board meeting, did either you or do you feel that you did actually get the right answers by the end, either from Mercedes or from yourselves, or is it still hanging? Oh, wait, there's something in the chat. Oh, yes. Oh, I see a yes in the chat. Wait. So you have the correct, you're, oh, great. Okay. I like how she's, okay. That's awesome. So great. Oh, well, that's going to save us a lot of heartache. Okay, wait, let me go back to the board here then. Okay. Okay, if that's the case, okay. Okay. Okay, so I'm about to turn the page. So this says where are current voltage and resistance coming from in the first place? Like what? I'm again, stop me if, but I'm taking from what Eugen said and what Jake said and what a couple other people said. I'm taking that you feel kind of now okay on kind of what happened with current voltage and resistance in the lab, and I'm not assuming perfect, but if you feel basically okay on it, I'm going to take that seriously and now back up and say, okay, like why is current flowing in the first place? Like what is the nature of current? I want to get at this. And you stop me if I've said this before. Okay. So I'm going to pause it. I'm going backwards into the origin of current in the first place. Let's imagine we have 2 point charges. I'm going to explain what I mean by that in a moment, but 2 point charges, well, two amounts of charge, 2 bunches of charge, of electrical charge, each concentrated into a very, very small, perhaps infinitesimal volume, perhaps Euclidean point. So we have a bunch of charge over here, and we have a bunch of charge over here, and they're but the bunches are very, very tightly packed. So like a little dot of some amount of charge over here and a dot of charge over there. I'm going to call them Q1 and Q2. I'm going to make one of them a capital Q and one of them a lowercase q, just to connote or just to imply the idea that probably one of them is a lot bigger in magnitude than the other, because if they're 2 arbitrary charges, what's the chance that they're both the same? And whichever one is bigger in magnitude, I'm calling capital one. And then whichever smaller, I'm calling lowercase. Assume they're separated by a distance r. Now, the distance r is measured in units of meters. Each one of these point charges are measured in units known as coulombs. Now, what is a coulomb? And in fact, what exactly do I mean by charge? I mean, we all sort of know and we all sort of don't. To put perspective on this, what you do, and tell me at any point if you need me to go back, obviously, what you do know, I think, from chemistry and from life, from 7th grade, you know that charge is some kind of property of matter that seems to be it seems to be manifested by or seems to characterize certain types of matter, particularly protons and electrons. Protons, like all matter, has mass. Protons they are material, they have mass, but they also have this property that we call positive charge. And one proton seems to be the smallest packet of charge that we ever find sitting by itself in nature. The smallest packet of positive charge. And an electron, similarly, is this small package of negative charge that we find sitting in nature. Now, protons and electrons are not the same size when it comes to mass. Proton is a lot heavier than electron, but they do seem to have an equal amount of this property that we call charge. Charge is measured in coulombs. It would be super convenient and straightforward if I were to just say, well, what a coulomb is a proton, and 2 protons is 2 coulombs of charge, and etc. But life is not that convenient. The truth of the matter is protons are extremely small in charge, electrons are extremely small in charge, and it takes a lot of them before we accumulate an amount of charge that's easily measurable or whose effects are easily observed in a laboratory, especially at the stage in history when this was first all being developed. So what it turns out, just to give you perspective on what this unit called a coulomb is, it turns out that the charge of a proton is called lowercase e, like the elementary charge of a proton is plus approximately 1.60 times 10 to the 19th, 10 to the negative 19th of these units that we call coulombs. This is the charge of a proton. Similarly, I should let you know that the mass of a proton is approximately, and I always get this wrong, it's approximately 1.67 times 10. I always get this wrong. I'm going to have to verify this. I always have a mental block on exactly this number. 1.67. 27. You can look it up on Google and verify. I'll verify in a second, but I'm pretty sure that's right. That's the mass of a proton. And now, just for perspective, the charge of an electron is the same, but opposite sign, as the charge of a proton. But for perspective, the mass of an electron is a far tinier number. Like, I'm not asking, by the way, I am not asking you to memorize any of these, but they are worth knowing and having. I want you to have perspective on like what we're talking about here. So it's not about memorizing, but it is about seeing the fact that the electron and the proton have the same charge in opposite directions, but the mass of a proton is like 4 orders of magnitude greater than the mass of an electron. 4 orders of magnitude, right? Like 4 zeros in terms of scientific notation, which means like 10,000 times bigger. Like the proton is like 10,000 times heavier than the electron. So these are very different types of things. But the charge of each of them is this tiny, tiny number, 1.60 times 10 to the negative 19th. What does that mean in English? What it means in English? Right. Okay. Yes. What I'm trying to say here, just for perspective, because we're gonna more people. Okay. We're gonna keep talking. We're gonna do all these problems and scenarios with like a coulomb of point charge over here and and 2 coulombs of point charge over there. What do we mean when we say this? Well, when we say a point charge, we mean a bunch of charge jammed together into a Euclidean point. When we say a coulomb, just for perspective, a coulomb is an enormous amount of charge. Well, or put another way, the things that carry charge carry tiny amounts of charge if we're measuring in the metric system in these units called coulombs. Like the charge of 1 proton is what it says here, like 1.60 times 10 to the negative 19. So going the other way, like 10 to the 6th is a million, 10 to the 9th is a billion, 10 to the 12th is a trillion, 10 to the 15th is a quadrillion, 10 to the 18th is a quintillion. So what I'm saying, I mean, I'm approximating here, but I'm saying then that to talk about a coulomb of charge is to talk about 16 quintillion protons. But to talk about a 1 coulomb point charge then is to imagine or consider like 16 quintillion protons jammed together into like the head of a pin. Now, that's hard to picture. I mean, maybe it's impossible to picture, but it's hard to picture because it's like 2 wrongs making a right. It's hard to picture because we're talking about such small objects here, but it's also hard to picture because we're talking about so many of those small objects. Well, we have to be talking about so many of those small objects in order to get to something that is actually macro, relatable in our world. So from now on, if I say a coulomb of point charge, I'm talking about a tremendous amount of protons jammed together into a little dot. And similarly, if I talk about a coulomb of negative charge, I'm talking about a bunch of electrons jammed together into a tiny dot. Can a whole bunch of protons be jammed together into a tiny dot? Yes, absolutely. Can protons, even more easily? Yes, absolutely. Okay, one last side note. I'll just, the truth is too, really, if you want to be realistic about this, protons, as you know from chemistry, are found in the nucleus of an atom, along with the neutrons, which have no charge at all, right? We got this nucleus of an atom, protons and neutrons are inside of it. And then outside in these orbitals or in these quantum orbitals or these clouds or whatever you want to say, the electrons are supposedly like orbiting around or clouding around in these probability waves. The point, and they're very far from the nucleus, comparatively speaking. So the truth of the matter is, electrons are comparatively easy to dislodge from their atoms. Again, I think you know this from chemistry. Electrons can fall off an atom and move to another atom, or fall off an atom and just move by themselves. I mean, this is called ionization, or atoms that are missing certain electrons or have extra atoms or extra electrons are called ions, right? Electrons can be moved around, can be ripped off the outside of atoms and moved around somewhat easily. So the truth is, from here on in, whenever I'm talking about net negative charge over here, I'm probably talking about a whole bunch of electrons that someone's ripped off of atoms and put over here, or nature has ripped off of atoms and put over here. If I talk about net positive point charge over here, probably what I'm really talking about ultimately in practical context is the absence of a bunch of electrons. The truth is, it's hard to play with protons. We don't generally play with protons. What both nature and we deliberately move around is electrons. And that's why this whole process that you've been studying in the lab is called electricity, not proticity or something. Because it's whenever we're talking about negatives or positives, we're really talking about electrons or the absence of electrons, just for perspective. But that is what we're talking about. Now, it turns out, again, stop me if it turns out, going back to this picture. Oh, is there one other number I wanted to give you? Oh, no, yeah, okay. Oh, there goes my board. Hold on one second. Sorry. Okay. Back to this picture, back to this picture. Yeah, if you have, you have a bunch of charge over here, separated by some distance in space from a bunch of charge over there. it turns out okay. But I'm going to pause for a second. I'm under the impression I have not told you this before. Stop me. Have I told? I don't think I've told you this before. I mean, you may have seen in other classes, but you've not seen this from me. Is that correct? Like, you like, no, that's correct. Okay. Okay. All right. So here's what I'm saying. You have any point charge over here, like, so any amount of charge, like 5 coulombs of positive charge over here. And then you have some other amount of charge, like over here, like -2 coulombs of like negative charge over here. So you like have a huge bunch of protons over here and some smaller bunch of electrons or something over here. And they're separated by a distance r. Evidently, one point charge will exert a force onto the other point charge it'll exert a so one point charge will automatically push or pull on the other charge with a direction that is determined by the nature of the two charges, like you know from chemistry. If they're of opposite charges, this will be a pull. If they're like charges, this will be a push. I mean, I'll write that out for you in a second. But so one point charge will automatically pull or push the other point charge with a direction that's determined by the type of charges they are, and with a magnitude that is determined by this equation, this law known as Coulomb's law. This equation, which says one charge will exert a force on the other whose magnitude is given by the magnitude of one charge times the magnitude of the other charge divided by the square of the distance between them, all multiplied by a universal constant known as the Coulomb constant, or known as the electrostatic constant, a universal constant which happens to be this huge number, approximately 8.99 times 10 to the 9th newtons meter squared divided by Coulomb squared. Okay. The force that one point charge exerts on the other point charge will be given by this whole equation, will be given by this constant times the magnitude of one charge times the magnitude of the other charge divided by the square of the distance between them. Now, this is a mouthful. certain aspects of what I'm telling you, I'm definitely am asking you to memorize. Certain aspects I'm not. Let's break this down. Um, okay. Hold on one second. One, pardon me for 1 second. Okay. So first of all, this K sub E, it'll be written different ways in different websites or different books. The reason I'm writing it K sub E is to make clear this is the third K that you have in this class. It has nothing to do with the other two Ks. It's like super unfortunate and inconvenient that we have all these Ks. It's just the way it is. But so I'm putting the lowercase e to try to make it clear. It's not the K that means angular wave number, and it's not the K that means Hooke's law constant, spring constant. It's just a different K, but it's called K. To be really truthful, in case if you go on in STEM or whatever, in life, sometimes K is also written this way. This is a little bit of a sidebar. I don't want to get bogged down in this. There's another way that K is often written. It's written as a combination of other constants of 1 over the constant 4 over the constant pi times this other constant called the permittivity constant epsilon naught. And epsilon naught is a teeny tiny number. If you put 1 over 4 times pi times this teeny number, if you put them all in the denominator, the whole thing equals up to this huge number, 8.99 times 10 to the 9th. You don't need to worry about that in this class. I'm just telling you, it's another way you might see this constant written, like in websites and in textbooks, etc. But the main thing is that it's just a constant. It is just a constant. We would not need this. It doesn't really, at least at this stage, have any real physical meaning or complexity. It's there to ensure that it's like a scaling constant. We put it in there to make sure that after we multiply Q1 by Q2 and divide by the square of R, we want everything to work out in units of force, i.e. newtons in our metric system. So this constant is actually there to ensure that the units of this constant may look very obscure and weird at this moment, like they are. They're newtons times meter squared divided by coulomb squared. You might think, is he asking me to memorize that garbage? Well, yes and no. I'm not really asking you to memorize it, but if you understand what I'm saying, you will automatically accidentally memorize it. Like, oh, there goes my board again, or it's about to disappear. The reason K is measured in newtons times meters squared divided by coulomb squared is if you look at the equation, Q is in coulombs, Q2 is in coulombs. So automatically you get coulombs times coulombs, that coulomb squared. In the bottom, you get meters squared. So the units of K are designed. The whole purpose of K is to cancel out those meters squared and those coulomb squareds and then just be left with newtons, which is what a force is. Okay, so I'm saying all of that I'm saying all this stuff about K, really to say don't get intimidated or distracted by the K. K is just a proportionality. There goes my board. I'll get it back. I don't know why that always happens, but I do, but I don't. Hang on, here it comes. Well, here it doesn't come. One sec. If you ever watch that YouTuber that I think has been canceled, there used to be a YouTuber named Gus Johnson who was very funny, I think, or at least my college age son thinks he is very funny, and he does this mockery of he did this YouTube called How to Become a College Professor, and he gets in front of a whole room and just messes up technology for an hour and 10 minutes, like super incompetently, and it's perfect. It's hilarious. It is exactly how to be. And of course, like I'm a science professor, and I still anyway. Okay, so where to go? Okay, oh, you do? Okay, you remember him? Awesome. I'm glad I'm not just. Yeah, he's hilarious, or he was hilarious. I know something went wrong, and like with everybody else in life, something went. But yeah, he. Oh, he did get. Oh, you both know him. Oh, I actually feel so seen. I feel so safe in this room. You both know who I'm talking about. It's great. Of course, I'm just trying to really. Okay, I'm sorry, he got. Anyway, but yes, that thing of how to be a professor is totally hilarious, I think, and spot on. Okay. You know who I really like? I can't say this, and I think this guy never got canceled. And I think one of the first YouTubers my son ever showed me, like when I didn't believe there were such things as YouTube, was Oh, now I'm gonna wait. Hold it. Ryan Higa. I think that guy is brilliant. I don't know if you know who I'm talking about, but oh my God, is he? I mean, whatever. Yeah, okay. I mean, he is hilarious. All right. Anyway, so I'm glad we're relating. And anything I know about any of this stuff comes from my 19-year-old son. Like it's not like I would have figured it out on my own, um uh but I think he has good taste. Okay. So everything I'm saying right here about Kay, oh sweet. Oh, Celine. I got Celine. Awesome. She's a lab tech, don't you know? Okay. I don't know why that makes me okay. Anyway, the 2.5 hour class, we'll do anything to keep each other going. Right. Okay. So so the constant thing is just a constant of proportionality. The real important thing to see here is what we're really trying to say is you know what? I'm going to write this on the next page. This is too ridiculous. It's too important to squeeze like this. I'm sorry. Hold on. See Gus Johnson. Okay, just to read what we have so far. So I'm saying, according to this electrostatic interaction, this Coulomb's law, according to it, any and every point charge, in other words, any and every bit of charge anywhere in the universe automatically, necessarily pulls or pushes on any and every other point charge anywhere in the universe with a force, like with a number of newtons, right? With a pull or a push, which is, so here we go, A directly proportional to the magnitude of each point charge, right? That's number one. So if you double, if you double the size of one of the point charges, you double the strength of the whole force. If you triple the size of the other point charge, you then also triple the size of the whole force, right? It's directly proportional to the magnitude of each point charge. Hello. Inversely proportional to the square of the distance between the charges right? So we're saying the bigger the charges, the harder they pull or push on each other. The closer the charges, the harder they pull or push on each other, right? We're saying that so far. C, we're saying, I keep using words like automatically or necessarily or something. I'm saying all this happens here's perhaps the most important thing. So this law, which we're saying is a law because apparently it's true, and I mean that, this Coulomb's law, like certain other laws of physics, not all, but like certain other laws of physics, we believe in it because it evidently, empirically, seems to be true. We didn't think that it should be true. We didn't predict that it would be true. We don't have necessarily an argument for why the universe needs for this to be true or that it should make sense that it's true, but it just seems to be true that for any point of charge you have in the universe, it'll automatically pull or push on any other point of charge in the universe. First of all, in a manner that's directly proportional to how strong each of the charges is. Okay, and by the way, maybe that seems reasonable to you. It sort of maybe is reasonable. And it'll pull or push on, and charge will pull or push on the other charge in a manner that's inversely proportional to the square of the distance between the two. Well, they might sort of make sense. Like, yeah, okay, I guess the farther away things are, the less they affect each other. Maybe that's not shocking. Why it's the square of the distance is certainly not obvious. Like, I'm not saying there aren't reasons, but if I'm writing this down for the first time to myself or to you, I certainly don't want to say, well, duh, of course it's inverse r squared. Like, I'm saying there's an r squared in the denominator. I'm telling you that's true. But I'm definitely noting, like, I don't know why obviously that should be true or why that's self-evidently reasonable. It's not necessarily, but it is the case. But then here's the third part about this law that's particularly noteworthy. What we're saying is this is a force, okay? This a force of attraction or repulsion between protons and electrons. We're saying it's a force, like any other force, like the frictional force, like the tension force, like the gravitational force, like the normal force. It is an interaction between two objects. It's one object pushing or pulling another object. It's a force that would go into the left side of F net equals NA, like any other force. Like, we can do calculations with it. We can predict accelerations from it, from anything we learned in Physics 101, right? It's a force. It's a regular everyday force interaction between two objects measured in newtons, yada, yada, yada. But here's the catch of this force. The force that a proton exerts on an electron, or that a proton exerts on another proton, evidently happens automatically. What do I mean automatically? I mean that for a proton to pull on an electron, the proton doesn't need to do anything. It doesn't need to move in any particular way. It doesn't need to send out a tether. It doesn't need to press up against or yank with a string. even more specifically, what I'm saying is for a proton to pull on an electron, they don't have to touch. They don't have to touch. There can be empty space between them. And it doesn't matter how much empty space there is between them, they'll pull on each other. In fact, granted, the more empty space there is, the less they'll pull. But as long as there's any amount of space between them, they will pull with some amount of pull. So they don't have to be touching. That's already a little bit like, huh? And then number two, there could be crap in between them. Like you could have a proton over here, an electron over here. Evidently, they'll pull on each other without trying to, or without touching each other, or without having any material medium between them to mediate or transmit this force. And yet, if that's not strange enough, it's also the case that you could put crap in between them. You could put a table in between the proton and the electron, or you could put a bunch of carbon or something or metal between the proton and the electron, and that won't stop this force from happening. The force, this is what I mean when I say automatically or necessarily or something like that. I mean that this force evidently exists as long as the objects exist. And it acts through empty space as easily as it acts through matter. And we don't need any matter between the two objects to convey this force. In all of so this is called, okay, so this fact so this interaction between charges is known as action at a distance, meaning, well, just that it just happens at a distance, at any distance. It happens through empty space. It happens without touching. Do we have any other examples of that in the world? Well, yes, we do. We have one other particularly big example of that. Okay. Uh, Actually, okay. I'm gonna write this on the next page. Sorry, I can do that again. Okay, the first thing I'm saying right now, before I go to the next page. Okay, what I'm saying right now is, and you may remember this from Physics 101, for any 2-point masses in the world, for any one given point of mass in the world, automatically and necessarily pulls on any and every other point mass in the world with a force measured in newtons that is directly proportional to the amount of mass of each point and inversely proportional to the square of the distance between the 2-point masses. And the whole package is multiplied by a constant of proportionality measured in newtons times meters squared per kilogram squared, since point masses are measured in kilograms, unlike point charges, which are measured in coulombs. What I'm trying to bring to your attention, and so gravity, well, what I'm trying to bring to your attention, I'll say this on the next page. Tell me if you need me to go back. Okay. So the first, I'm going to maybe pause for a second, but the first thing I'm trying to bring to your attention is that the way in which protons and electrons attract or repel each other is mathematically precisely the same way that masses, point masses, attract each other. Charges come in 2 varieties, plus or minus. Masses only seem to come in 1 variety. So that is an interesting, that's a sidebar distinction between the two. Or put another way, gravitation is always a pull, where it's always attraction, whereas electrostatics can be attraction or repulsion. That's interesting, and I don't know why that is. I mean, and I'm not trying to blow it off. Like, that's interesting. That is a distinction. I suppose there are people that spend their whole lives trying to work through that. I know for a fact that there are people that spend their whole lives trying to work through like why that is. I don't know what to say about that, but putting that aside for the moment, like what is more to sort of topical for us is that we've got these 2 fundamental forces in the universe, these 2 fundamental forces that seem to be sort of holding together or keeping apart the universe. These 2 fundamental forces are known as fundamental because of the thing I said before, because they don't require any activity to kick them into gear. Like, unlike the tension force, where you have to pull on a string doesn't just automatically exert tension. If you put a string on the table and you don't tie one end of the string, to a pole and the other end of the string to another pole, or hold on to it or something, string doesn't just automatically exert tension. You got to do something with it or to it for it to do that. And friction, is a force that the tabletop exerts on an object that you're sliding along the tabletop, but you got to slide an object along the tabletop for friction to kick into gear. Like the two objects have to touch each other for that to happen. But these two forces, the gravitational and the electrostatic, no one has to do anything for them to happen. They just happen. And they happen through empty space, it seems. So we call them fundamental. They're just there, the glue of the universe, or the glue and the repellent of the universe, just doing their things as long as there are things in the universe to be doing this. They both have the same mathematical form. That is noteworthy. The two forces that we are studying so far at this point, or that we know of at this point in history, that pull or push through empty space, are both dependent on the square, or inversely dependent on the square of the distance between two objects. That's noteworthy. I'll just say I don't know if it's a coincidence or not. I mean, I do know, but it's certainly noteworthy. I'm going to pause for a second. So first of all, are you with me? So can I just get, well, let me forget confirmation again. This speech I've not given you, right? You said that already, but I'm just making sure none of this. Oh, Marina. Oh, that means, oh, thank you, Marina. And thank you, Sulady. You're saying, I just make sure, you're saying, yes, I've not given you the speech before. And yes, you get the speech so far. Like, that's what you're saying. Is that correct?
So far, yes.
Okay. And even if it's not totally clear, it is new, right? Like that. I'm just totally making sure. I don't want to waste right. I mean, it's new to
right. Exactly.
Okay. All right. Cool. Thank you both. Thank you. I'm getting all kinds of people. Okay. Okay, so I'm going to go on for a little bit. I will. Whoa, hello. Sorry. Okay. I always say that I'm not just going to talk for 2 hours. I really will try not to, but okay. Okay. Hang on 1 second. Okay. Okay. What I want to tell you, let's put it in perspective here. Our ultimate focus in this course is the electrostatic in your circuits. Ultimately, they're moving around. These negative charges are moving around in your circuits because they're being pulled by banks of positive charges on one terminal of the battery. And you probably know something about this from 7th grade or something. Like the idea of a battery is that we deliberately have a pole with a whole bunch of extra positive charge, and then we have this other pole with a whole bunch of negative charge. But there's insulating, there's non-metal, non-conductive material between the two poles. So the protons over here, the electrons over here want to get to all the extra protons over here, but they can't go straight across because they're blocked. So then we take this piece of metal known as a wire and we attach it from one pole to the other. So we allow a path, or we allow a conductive path of some material through which free electrons, dislodged electrons, seem to be able to move freely. And so the electrons from this pole start flowing through the conductive material to the other pole, to the pole with the extra protons. And that can happen randomly all the time. I mean, that can happen even just when even when you like accidentally rub your sock against the carpet and then you touch a light switch. Like, charges can flow from an extra bank. Negative charges can flow from some extra pool of electrons that get gathered over in one spot to some extra pool of protons that gets gathered in another spot. That happens spontaneously a lot. Sometimes it's like a little spark that you feel with your finger. Sometimes it's a big spark called lightning that goes, from moisture in the air to the ground. But usually when that happens spontaneously like that, what we sometimes call static discharge or something, usually what happens is a bunch of electrons will move to the place where there's extra protons, and then they get there and then they're happy, so they sit and the process is over. Usually a spontaneous discharge like that leads to equilibrium and then gets settled and is over pretty quickly. The whole idea behind a battery or a voltaic cell is that a chemical reaction deliberately continues to replace the electrons that have left one pole for the other pole. A chemical reaction keeps depositing more electrons onto one pole so that you have this pole that steadily, continually has extra electrons on it, even as some leave to go join the protons on the other pole. So the whole point of a battery is that it is a continually, or until it runs out of the chemicals, it's a continuously self-replenishing supply of net charge asymmetry. And so we get these charges flowing through the wire known as current that you've been studying in the lab. I mean, that's a very, very big overview of what's going on, obviously, and it doesn't help you with all the details that you've been grinding through in the lab. But that's like the larger thing that's going on is electron repulsion and attraction. What I'm trying to emphasize right now for the purpose of the course, what I'm trying to emphasize in lecture is that this electron repulsion and attraction that goes on is through empty space. And that's a very big deal. That has a lot of implications for us as experimentalists, but also as theoreticians. Hold on, I'm losing my, okay. Yeah. What I want to say is the electricity stuff that we're doing, the Coulomb's law, I should have written in the notes, the Coulomb's law is from the mid-1800s. It has the same mathematical form as this gravitational law of Newton's that was developed in the 1700s, or really right around 1700. And when the law came out, or even shortly before the law came out, when Newton wrote F equals gmm over r squared, again meaning that any one bit of m over here would pull any one give of m over there through an empty space of r in a manner that was inversely related to the empty space r. When Newton came out with this, it was not immediately obvious that that should make sense at all. Quite the reverse. Like, the claim of this law, of the gravitation law, and therefore of the electrostatic law, the claim of the law is that one object can affect another object through empty space, that one object can pull or push another object through empty space, and not just affect it sort of approximately or roughly or qualitatively, but the claim of the law is a mathematical law. It's an equation. So it's saying that one object can affect another object in a very precise, measurable, numerical way through empty space. And this is such a weird idea. It's such an important idea that I need to pause for a second. This is the curriculum. This is not off the subject. Like, the subject is, I want to read you something. In fact, I want to screen share something. Well, here, I'll screen share it right now. Hold on a second. Yeah, okay. Yes, okay. And again, if I've done this before, tell me, but I don't think, but my impression is that I have not. Here's the deal. And this is, again, this is like this is very important. So Newton's law comes out. At the time, you've all heard of Newton, I know that. What many people have not heard of is there's this guy named Lord Richard Bentley, okay, who was, so this is shortly before 1700. Lord Richard Bentley was Newton's mentor. He was mentor to many of the great thinkers of the time. He, just like Newton, is our teacher. I mean, Newton had teachers, obviously. And one of his great teachers was a teacher, was a don. He was like what they called a don, like a top administrator, like a senior. What do we call it now? I don't even remember what we call it now. Like can't believe I can, like a full professor, but more than that, a distinguished. He was like a distinguished professor at Cambridge and had taught Newton, and was the brains behind the brains to many of Newton's contemporaries. Well, at the time that Newton's thing came out, a letter was written to Newton's teacher, Lord Bentley. A letter was written to Lord Bentley, and that letter written to Lord Bentley by a physicist of the time, by a scientist, by an early physicist of Newton's era, a physicist wrote to Lord Bentley critiquing this law of Newton's. And I know you can see on the screen. Well, sorry. So regarding Newton's law of universal gravitation, and regarding this premise of a force that can be exerted without any touch, one early critic observed the following. So, okay, this is an excerpt from an actual letter that was written to Lord Bentley. Lord Bentley was British, so unlike Newton's actual work, I believe this letter was written in English. If not, it was written in Latin and translated, but I believe it was actually written in English. And here's an excerpt from it. It's famous, as you can imagine. The letter says, "It is inconceivable that inanimate brute matter should, without the mediation of something else which is not matter, operate on and affect other matter without mutual contact." Right? Like, it's a lot of words, but let's break down for a second. I mean, it's saying, if you look at just that sentence, it's saying it's inconceivable that inanimate matter should affect other matter without touching, right? That's what it's saying. Like that, with that clause in the middle, without mediation of something else which is not matter. It's saying you can't have stuff over here affecting stuff over there unless there's something in between mediating the effect, transmitting the effect, initiating the effect. It is so far it's saying it's inconceivable that inanimate brute matter should operate on and affect other matter without touching, without mutual contact, right? So now it goes on that gravity should be innate, inherent, and essential to matter. Now these are words like the words I'm using, like fundamental or automatic, right? When he says innate, inherent, and essential to matter, it means, like, if you're going to believe Newton, if this equation is supposed to have us believe that a piece of matter, a piece of mass, should automatically, by virtue of just existing, should innately, inherently, in and of itself, just have this property called gravity, that Newton's equation is, like, for the first time, putting forth to the world in 1693, that gravity should be innate, inherent, and essential to matter, so that one body may act upon another at a distance through a vacuum, meaning through empty space, right? Without the mediation of anything else by and through which their action may be conveyed from one to another, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Okay, so first of all, okay, they are saying no man, substitute the word. I mean, that's what they said. I mean, that's how they talk then. And, what, I don't know what to say about that, but substitute the word human is to me so great an absurdity that I believe no human who has in philosophical matters a competent faculty of thinking can ever fall into it. Now, let me make clear to you, I'm sure it is clear to any of you who are still with me, when he says competent faculty, he doesn't mean well-educated bunch of professors. They don't mean faculty like that, right? Competent faculty means like functioning mechanism, right? So he's saying that if you look at just the big print, I know I'm yelling, I just want to get this across. This is a critique of Newton. Like, Newton's our hero, right? Like, Newton is the guy that all of this physics is coming from in the first place, or not all of it, but the huge amount of it is coming from in the first place. And Newton comes out with this universal fundamental equation that we use to this day that put men on the moon, put humans on the moon, but honestly, I think it was men that were on them if the moon landing did happen, which I do believe it did. We could talk about that later. But this equation that comes out from the supposedly great Newton, like, this guy is writing to Newton's teacher and saying that gravity should be innate, inherent, and essential to matter, is to me so great an absurdity that I believe no man who is at all competent at thinking could ever believe it, right? That's what he's saying. I mean, he's saying this is moronic. He's not just saying, I think it's wrong. He's not just saying, I think Newton forgot to carry the two, right? He's saying, I think this is absurd. This is idiotic. And what is this? Let me remind you again. I'm going to turn it over. I know I'm yelling. I'm going to like bust a gut. I'm going to turn it over to you guys in a minute in more ways than one. But I want to make clear that that this guy is talking about is the idea that something could affect something else through empty space, right? That he's saying, come on, are you kidding me? Like, you're not just saying that, Newton. You're not just saying that sometimes it happens, but you're saying it's a universal law. Like, this is the way nature always works, that crap over here is pulling crap over there automatically without touching it or doing anything. Just like, hello, I'm here, you're there. Come to Papa. That's what you're saying, Newton. And this guy is writing to Newton's teacher and saying, dude, that this is absurd. Okay. And obviously the person who wrote this was important enough that the letter survived. And even though you haven't heard, I mean, well, maybe you have, but even if you haven't heard of Lord Bentley, like, the letter survived. So somehow this made a difference somewhere. Now I'm going to pause for a second. I'm going to unscreen. Well, and by the way, I think if I didn't already put this PDF in your Google Classroom, I certainly will. Like, you'll have this to keep, of course. But I'm going to I'm going to unshare for a second because I want to have a discussion about this, and I will even stop my board. Hold on a second. I'll put my board. Okay. So wait, first of all, just raise your hand if you you get the point. Like, do you understand what I'm saying so far? That someone objected to, you get what's being objected to? Okay, Ashton. Okay, thank you. And I think, Jake, I see your face. I think. And by the way, the black and white is very film noir. I mean, it's very like, okay, cool. Okay, and thank you, Eugene. I see your thumb, and you're all. This is like, so Jake's in black and white, and Eugene is like an aerial. Okay, I shouldn't be. You guys have enough guts to actually show video. Now I'm gonna make fun of, like, what am I, loser? But no, it's very okay. But cool. I love the. Okay, so at least 3 people are with me. You all get. So the objection here is action at a distance for, and thank you for the shout out, Ashton. Like force acting through empty space. Now, I'm going to tell you. We're going to have 2 kind of discussions about this. Again, this is not a sidebar. Like, this is the point. This is like why we're paying tuition, whatever. First of all, the person who wrote this letter objecting to Newton was a physicist of the day. You have heard of this person. I know for a fact that you know of this person who wrote the letter. Okay, I'm not saying it's easy to guess, but I'm saying you do know who the person is. So I'm going to, so assuming you understand what the objection is, wait, okay, no, I'm going to do this. Put your electronic hands up if you basically get the if you basically understand what is being objected to. And keep them up, please. I want to sort of wait till I have a actual full house. Oh, thank you. Cool. Thank you, Remy. Thank you, Devin. Thank you, Abigail. Thank you, Eugene. I see that. And okay, cool. Thank you guys. But Giselle, Isabella, Kayla, I'm not trying to call you out. I just want to make sure everybody's together. Like Sule, Ariana, Sylvia, you get what do you like, or do you want to ask a question in the chat? Do you, or Marina, like you get what? Okay, Sule, can you just placate me for a second? Giselle, thank you. Okay. Okay. I guess that's good enough. That's a quorum anyway. Okay. I mean, I guess if the government can function on that, we can. Oh, wait, the government doesn't function. Oh, wait, did I just say that? Okay. And I meant that in the most nonpartisan way possible, I promise. So here's my question. Here's where I'm throwing it to you guys. If you're following this so far, and I'm not, this is not a test, this is for the purpose of discussion. Can you please, in the direct chat or however you want, can you offer some guesses as to who might have raised this objection? And Remy, and Remy, is that it? So Remy, you're raising your hand that you get it, or you're okay. So I would love to hear, either in the direct chat or even with voice, like some guesses as to who wrote this objection to Lord Bentley. I'm not assuming you've heard of Lord Bentley, but I'm telling you that the guy who wrote, and it was a guy, I mean, it was just because that's the way it was. Which, by the way, is not to say that there weren't intense women at the time who may well have had a very reasoned objection to this. It's just that people wouldn't have kept their letters with quite the same vigilance that they kept them. I mean, that, right? I mean, I don't know what to say, but although I'll also say on the sidebar, I will say this. You know, I act like my hero is Newton. My real hero is Galileo, even more than Newton is my hero. And for what it's worth, if anybody's ever interested, I just feel compelled to make this sidebar. So Galileo is like one of my heroes. Galileo's amazing. I mean, Galileo's not an amazing person. I mean, he was like a drunk. I mean, you know, he had his issues, and he had like 3 children out of wedlock, which was a big deal at the time. And 2 of them were women, which he then did the most respectable thing he could do, or thought he could do at the time, with these daughters that he had out of wedlock. He sent them to a convent so that they could live a seemingly respectable life and not live with the cloud of shame hanging over their heads for being illegitimate daughters. I'm saying all this just as a thing of history, but reason I'm saying it, for what it's worth, if anybody's interested, one of those daughters that he sent away to a convent, seemingly to protect her, I guess, whatever, he did. That one of those daughters that he sent away to a convent was clearly a genius and maintained a relationship with him through letters. They wrote back and forth letters all the time, and she was evidently instrumental in his work, like as a muse from a distance. They had a letter writing correspondence that is phenomenal and brilliant and very, very important. And all the letters in one direction survive. The letters that she wrote to him survive because he kept them, and then his stuff survived. Her letters were all burned or whatever because they were in a convent, and that's the way it was. But her letters are all collected in a huge hardcover volume called Galileo's Daughter, and they're amazing. And she's clearly amazing, especially given what her life was like. And she had a huge influence on his work. Just say, for whatever it's worth, Galileo's Daughter was a major physicist to the extent that anybody could be in a situation like that. And clearly she would have been if the situation had been different. So again, just for whatever it's worth, like she's a jewel of history that is worth looking at if you care. But okay, that's a total sidebar because I'm embarrassing myself with all this like gender language and stuff. So what I want to ask you now is, you do know the physicist that you do who wrote this objection to Lord Bentley, and it was a he, but you have heard of him, and I want you to guess who it was. Okay. And I'm going to look in the chat to see what you've guessed. Okay. So I'm looking in the, so people are with me. That's good. I'm seeing in the chat that at least people are with me. Thank you. And we're playing this guessing game for fun because I mean, for fun. Like, it's not a test, but I'm curious. Okay. So I've got, no, and yeah, be honest. Like, there's no reason you would know. We're playing this guessing game for fun. You'll see why it's just for fun. So one person is guessing Niels Bohr. Totally reasonable guess because you've heard of him in science. He's a major guy in science. And you're right and Niels Bohr actually turns out comes a little bit later, but you're right that Niels Bohr is like certainly dead now. I mean, he's from history. and I don't expect you to know all your names and dates and stuff. So Niels Bohr, and in fact, Niels Bohr had a lot to say about like atom structure and stuff. So it's a very reasonable guess, very reasonable, educated guess. Shows someone who's been studying science for a few years, but it's not Niels Bohr. Good guess, but not. Okay, cool. I thank you, Kayla, for what you said about that. Oh yeah, she was totally a woman in STEM. Obviously, they didn't call it, and she was a woman in STEM, who lived in isolation. I mean, whatever. We could go on about that. I mean, I feel bad for you guys that you have to learn like not living in dorms and like learning electronically on Zoom. But can you imagine literally? Anyway, yes, she was totally a woman. Von Braun. That's a really interesting guess, actually. That's not correct, but that's a really interesting guess. Fermi is also a really good guess. Okay, I'm skipping around. I'm just looking. Hooke. So someone wrote Hooke's Law and then wrote they don't know his first name. But Hooke, as in Hooke's Law. God, I don't even know if I know his first name, actually. I should. That's an amazing guess. Let me pause for a second and just say, Hooke is a great guess for a number of reasons. Number one, okay, we totally learned about him in this course, so it's totally reasonable for me to assume that you know who he is. Number two, it totally is the same era as Newton. Not that you would necessarily know this, but it's true that Hooke was living in the same era as Newton. And in fact, you may or may not know, Hooke was a major rival of Newton's. He was. It's absolutely reasonable to guess that Hooke would have had a major objection to something Newton said, and that he wrote it down. In fact, sidebar, not exactly sidebar, part of the point of the course, Newton was one of the people in history who was a very firm believer that light was made of particles. I think we mentioned this last time or 2 times ago. Whereas Hooke believed that light was an example of wave motion. They totally debated over that very, very, very fundamental question. So it's absolutely reasonable to guess that Hooke would have objected to Newton's gravitation. And in fact, by the way, I don't know that he didn't. It happens to be the case that he wasn't the one that wrote this letter. But Hooke is a great guess and totally shows that you're in the class. Hold on. Yeah. No. That's great. I'm not mentioning names, but the person who guessed Hooke and gave a reason for it, very good reason and very good guess. Now, and I'm intentionally going out of order in these guesses. Someone saying a pope. That's a great, no, that doesn't sound weird at all. It's very reasonable to guess that a pope would object. Wow, that's a great guess. It's totally reasonable. Just like just like definitely Galileo got into major skirmishes with the Pope at his time, which was Pope Gregory the 13th, I think. And also Pope Pius, whatever. Yes, very reasonable to think that a Pope would get into the fray and perhaps even write letters objecting maybe to Newton's teacher. Very reasonable guess. Also plausible, not actually the author of this letter, but by the way, I don't think I've had someone guess that in any. That's a new guess, but it's a very good one. And now people guessing, no, and fair enough. And someone's saying like, LOL, I'm just naming off people who are scientists. I know, fair enough. Like, why not? And by the way, guessing astronomers such as Kepler, which someone's guessing is, Robert was Hooke's first name. Great, thank you, Jake. That's awesome. Okay, I should have known that. Someone guessing Kepler, also very good. Also very reasonable time frame. Kepler is a little bit before Newton, but in fact, they overlap. Kepler, very reasonable guess. I mean, it turns out Newton based a lot of his work on Kepler, so maybe they were slightly more in harmony than some, but very reasonable guess, also not the case. But awesome. And I'm glad that everybody really is participating in this. Now, wait, I think I know a couple of you have guessed someone that I have not read out loud, and I know that, and I will in a minute. Ingoli. I'm not even sure I know who that is. Ingoli. I'm so embarrassed. Maybe I don't know who that is. I think it's probably a really good guess, especially you're guessing something that I don't know. I mean, how sophisticated are you? Oh, how obnoxious am I to assume that if you're saying something I don't know that you're sophisticated. But oh my God, I totally thought Eugen had actually transmogrified into I thought that was a creature, but it's a chair. Okay. Ingoli. I don't know if I know who Ingoli is. But that's cool. And if you want to explain, that'd be great. And Fermi, I love Fermi. Fermi's another great guess. A little bit. He's later. I mean, he's more contemporary, but okay. I'm going to say this. I've definitely gotten, if anybody else wants to guess, that's awesome. But I've gotten so many guesses that I'm willing to say now. I will say that 2 people in direct chat did put an answer that I did not read out loud. And I'm kind of amazed that 2 people put this. And shout out to them. 2 people in the direct chat actually guessed Newton. And that's actually right. And let me pause for a second on this. I'm not trying to trick you. I'm doing this for fun. I mean, I think it's fun. I'm not trying to make you feel stupid or something like that. Like, far from it. But the answer is Newton. And the reason I'm doing this is, oh yeah, that's weird. Like, let me back up and make it clear. Yes, I mean, I've set us up for this like little primrose path or whatever, but it blew my mind when I first heard this. Like, that objection that was written to Newton's teacher, that objection to Newton's law was written by Newton, and he wasn't kidding. And he privately wrote it to his teacher because he was starting to go crazy. And eventually he did basically go crazy over this. Let me explain. Newton is saying, and he knows he's saying, like, Newton is about to publish this law. And in one part of his brain, he's like, this seems to be the way it is. But in another part of his brain, he's saying, that can't be. But the first part of his brain is saying, that's what the data seems to suggest. Like, when I run all the numbers of particularly of astronomical orbits, of planetary orbits and eclipses of moons and stuff, when I put together this vast amount of astronomical data that is largely coming from, as some of you said, Kepler and Copernicus before him, and Tycho Brahe and Galileo, when I take this enormous amount of astronomical data and start looking at the patterns of the planets going around the sun, which we now believe is going on in the last few years since Galileo, and I put together these numbers and I relate them to what seems to be happening when objects fall toward the surface of the Earth, according to Galileo, it seems like there's this one overarching statement that captures all this data that seems to consistently account for all the measured data that we have so far, and seems to make predictions of new things that we hadn't yet known. Like, it seems to make predictions of, for example, planetary eclipse, lunar eclipses of like the moons of Jupiter, things that people didn't know about before and couldn't have made predictions about. Like, they didn't even know Jupiter had moons until Galileo's telescope. So Newton puts together this stuff and comes up with an equation that works scientifically. It accounts for the data accumulated thus far, and it predicts new data that we didn't have until that equation. And then the predictions are verified. So he's got this equation that works scientifically, but it makes no sense. Well, let me say this again a different way. It works physically, but it makes no sense metaphysically. It makes no sense, or seems to make no sense philosophically. It seems to account for the data, but does not seem consistent with any preconceived notions that we might have had about how the universe should, or seems like it would, work. What Newton's saying is, here's math that seems to make numerically accurate predictions, but the math seems to imply that crap affects other crap without touching it. And I never, ever would have thought that crap could affect other crap without touching it. So my mind is split in two. I am aghast at myself. I don't know what to do. What he did eventually was let the equation out. Now, he wasn't actually a big publicity hound like many scientists. The truth is, he kept these equations in his attic for a long time, partly because he was so disturbed by them. But he eventually did release them. And part of the reason, and in my judgment, part of his releasing this equations really marks the beginning of science as we know it, science splitting from philosophy and saying from here, because, once upon a time, people just thought about stuff. And they called it philosophy. And when they were talking about government, they called it political philosophy. And when they were talking about space, time, and matter, they called it natural philosophy. But they just wrote and talked about stuff. But around this time of Galileo and Newton, what starts to happen is a split. And Newton eventually goes with one part of his mind and says, you know what? If I'm going to go down the road of what we're now calling what we used to call natural philosophy and what we're now calling science. I'm going to go with, it's about objectivity, lack of bias, and data collection so seriously that even biases that I didn't ever think of as biases, that I just thought that's the way the world is, I have to be willing to get rid of. If the data says GMM over R squared, if the data says stuff affects other stuff without touching, I'm going to have to go with stuff affects stuff without touching. And the fact that I don't like it, may bother me as a philosopher, but if I'm going to be a scientist, I'm not allowed to like or not like. It's not about my opinion, even if I didn't even know it was an opinion. I just thought it was a basic assumption about life, but it's an assumption that stuff can't affect other stuff without touching. So if the data contradicts it, I don't fit my data to my assumption. I change my assumption to my data. This is science in its deepest form. And it's so deep that Newton did. There's more to this letter where he eventually says, how this could possibly be true, I must leave to future generations. And the future generations involved Einstein. Like this confused us all. Like this idea that crap could affect other crap was left lingering for a long time. I'm going to go back to the board now and be more specific. Hold on. Oh, wait, sorry. So, I mean, if you interpret, so what's the upshot of what I'm saying? If part of the upshot of what I'm saying is if you think, well, Newton's a crazy man, I would say, yeah. If by crazy you mean he had two voices in his head that were equally loud, yes. But I would also say it's crazy not to be crazy, right? I mean, if he thinks about this enough, if he thinks about the way the world seems to work and tries to match it up with the way he thinks the world should work, he goes crazy. And he really sort of did by the end of his life. But if he doesn't think about it, if he's just like la-di-da, if he's like, well, I mean, all the data seems to suggest this, but I always thought stuff should have to touch other stuff for it to affect. So I guess I'll throw out that data. Well, that's crazy too, right? It's not clear what what you get my point. So hold on. I'm just going to go back to the board. We're going to start. So what am I doing with this? I'm saying, whoa, science is messy. And the real deep thinkers think so deeply that they do not think the way textbooks make it seem like they think. It's all cleaned up after the fact. It's not clean while it's happening. But also, more specifically, to be more concrete. So partly I love that, as you can tell, just as a piece of history, I love that happened, that Newton literally wrote a letter objecting to his own, violently object. I mean, he's literally saying like anybody who thinks this is an idiot, but like it's him that's thinking it. So, okay, that's what it was like to live with Newton. But now more specifically in terms of the science that we're trying to do, like what do we do with that? We have to go a step, we have to say, well, what is so wrong? What is really so problematic about stuff affecting other stuff without touching it. Like, okay, like I would have assumed, I suppose, if you just asked, I wouldn't have known that I was assuming it, but subconsciously, I would have assumed that for something to affect something else, it's got to touch it or somehow, yeah, touch it, somehow be in physical contact with it. But why would I assume that? I mean, after all, I do see things falling. I do see that the earth pulls stuff down. I have gotten used to the idea that all things seem to be pulled toward the center of the earth. And I've seen magnets, which we haven't talked about yet. But like, of course, I know we've all seen magnets. So we all have some experience with things pulling on or pushing on other things without touching. So like, why am I making a big, like, why is this such a, I mean, if we're so used to it, like, why would Newton be that disturbed by it, or what is so disturbing? Well, one reason I want to say is, magnets, we've all seen them, but come on, we all love magnets when we're children. I mean, the reason magnets leaps to everybody's mind whenever we talk about action at a distance. I mean, I hope magnets do leap to your mind. If I say something affecting something else without touching, often people will eventually think, well, wait, isn't that what like magnets do? And they're right. That is what magnets do. But that's precisely why magnets are so much fun and so fascinating, because it's so weird that they do that, right? Like if you want to do a magic trick and have something seem to affect something else, like in a ghostly, weird, inexplicable manner, you use magnets, because magnets do provide this effect that is very unusual. I mean, it's usual for magnets, but it's very unusual for the world. So number one, just on an intuitive level, it is like a little bit jostling when something pulls on something else without touching. But now number two, scientifically, quantitatively, here's the real problem. Wait here, I'll write this better. 1 second. Okay, I'll read this out loud because my handwriting is obviously a disaster. Okay, what I'm saying is, recall, action at a distance is a precise quantitative, that should say, quantitative prediction. Action at a distance is a precise quantitative prediction or statement or description, whatever. The pull or push exerted by one object is quantitatively determined by information describing the other. This is what I... or So everything I'm saying right now, please understand, everything I'm saying about action at a distance applies equally well to gravitation and to electrostatics. The actual subject of our course is electrostatics, but electrostatics works just the way gravitation does. Gravitation is often easier to pick. Gravitation is like between masses, ultimately between like stars and planets, or planets and moons, or planets and stuff on the planet. Like it's about masses. Electrostatics is about protons and electrons. We ultimately care about protons and electrons, like in the lab of this course and everything. But masses are easier to picture. So you do whatever you want in your mind. I keep referring back to gravity because it's the more concrete thing to visualize. But any claim I make about, and it's the first one in history to be sort of investigated this way. So whatever I say about one applies to the other. So what I'm saying is this. I want to be quantitative now, or I want to be more quantitative now. According to gravity, the sun is over here pulling on the earth that's over there. According to electrostatics, a proton is over here pulling on an electron that's over there. Hold on, I'm just going to change the view of the screen for a minute. Sorry. Okay. Like according to electrostatics, Coulomb's law, a proton over here is pulling an electron over there. Okay. But according to the actual equation, according to the details of the law, the proton, or the bunch of protons over here, is pulling on the bunch of electrons over there with a precise number of newtons that is precisely determined by how many protons are here and how many, but by how many protons are here and how many electrons are there and by how far apart they are. So let's be more, so the proton, I keep so disoriented looking in the mirror. The protons here are pulling on the electrons here with an amount of newtons that's affected by how many electrons are here and how far away they are. So, okay, let's say the protons start pulling on the electrons. So the electrons, and let's assume this is isolated, either we're just two bunches of charges somewhere isolated in the lab or far, far away in outer space. Like, let's just assume there's not a lot of other stuff around to interfere with this thought experiment. So you got protons here pulling on electrons here. So they exert a force, a certain amount of newtons, 50,000 newtons, let's say, and they start pulling the electrons. So there's nothing else going on. So the electrons start accelerating toward the protons and start moving in. Now the electrons are closer. Okay, now the electrons are closer. But now that the electrons are closer, according to this law, the pull that these protons is exerting, now I'm going to pause and ask you, if the electrons are now closer and all other things are equal, if the electrons are now closer, are the protons now pulling harder or softer? Are they pulling with a greater number of newtons or a lesser number of newtons? I'm going to wait till you answer just so I can make sure we're all together. Just put something in the direct chat. If electrons are now closer to protons, are the protons pulling with more newtons of force or less newtons of force? Please put in the chat. I'll say it again. Protons are pulling on electrons through that equation, KQQ over R squared. That's good. That's one person. That's one person in the chat. Thank you. And by the way, I think the answer is right. So if that's encouraging to anybody, I'm going to say the question, but thank you, one person. I'm going to wait till I get three. I'm going to, that's two. That's great. And that's also the right answer. That's two. Should I say the question one more time? I love this class. Just when I'm about to feel super awkward. I'm going to say the question again. I've got two people so far, and they have the correct answer. Protons over here are pulling on electrons over here through KQQ over R squared. They pull on the electrons start getting closer. The R, in other words, gets smaller. Does the whole force get bigger or does it get smaller? I'd like one more answer in the direct chat, please. Oh, I think there's. Awesome. Okay, I got two more answers in the chat. Thank you. That's good. So now I have four answers in the chat. Five answers in the chat. Great. You're totally paying attention. Thank you. Okay, now I'm going to say I actually didn't get all the same answers, so I'm going to be clear what that's good. That's five. Thank you. So I think the answer is actually bigger. Like so, and please now, I'm not trying to shame anybody. I'm going to say it. If you don't understand what I'm saying, tell me in the chat. The equation I'm looking at is this. I'm looking at this equation here, the black one. F equals KQQ over R squared. I'm saying we got Q over here, we got Q over there, and there's R between them. So the Q starts pulling. Yes, good. I see in the chat. Okay, right. Because R is in the denominator. And this is what the equation means, right? R is in the denominator. So the force that the proton exerts on the electron, the force is inversely proportional to the square of the distance between them. No, it's fine. It's totally fine. But thank you for participating. But you get it now, right? Both of you get any of you. Yeah, okay, cool. Right. So since the R is in the denominator, the force is inversely proportional, and it happens to be an R squared in the denominator. I'm not asking. But okay, cool. In fact, actually, yeah, let's practice a little bit. This is usually on the final. So let's practice for a second. What this is saying is, if the electron gets twice as close, if it's twice as close now, then the force will be 4 times as great. Does everybody see that, right? Or if the electron gets 3 times as close as it was before, I'm saying it in a weird way, but if it's like a third as close, then the force will be 9 times as great. The force is inversely proportional to the square of the distance between them. People are with me? That's the mathematics of it. But now think about the conceptual implications of that. The proton's sitting here, reaching out and pulling on the proton with an exact number of newtons, somehow through empty space. Now the electron gets closer. The force adjusts. The proton adjusts its force. The electron is closer according to this math. It just looks like math, right? It's just like an equation. But if the equation is really true, if it's really describing the physical world, then what it's claiming is that as the electron gets closer to the proton, as the amount of distance of empty space between them shrinks, the proton adjusts its pull and starts pulling harder and harder. It's saying, like, if you just think of it as math, yeah, R is the input and force is the output. But if you think of it as a physical process, which is what we're claiming it is, what that means is that the amount that I pull on you changes as you get closer to me, or frankly, for that matter, if you got bigger, if suddenly someone added another electron to you, then I'd be pulling harder on you. But you're over there in empty space. You're getting closer to me, and I'm pulling on you harder because you're closer. But not to put it too crudely, how the hell do I know that you got closer? Let me put it more specifically. If you get closer, if you get twice as close, I start pulling on you 4 times as hard. If that's true, that has to mean that I, the proton, have received the informational update of your new address. No joke, right? I have to know that you are closer for me to pull on you harder now. Now, I hate the word no. Don't get me wrong. I'm not trying to be silly. I don't mean that the proton is consciously thinking about it or having feelings about it. I'm not saying that. But I am saying if the proton exerts a pull in a number of measurable scientific newtons of interactive force, if it exerts a pull that is determined by how far away the pulled object is, then that means whenever the pulled object changes its location, the puller somehow receives that informational update. It receives the information. How does that happen? Do you see what I'm at? Wait, first of all, I'm going to check. Oh, sorry. Okay. Sorry. Okay. Everybody can hear me on the 3rd floor. Sorry. They can receive the information. But wait, first of all, just raise your hand. Do you get why that's weird? Do you get what I'm saying? Maybe not. Should I say it louder? I'm just kidding. Okay. Thank you, Ashton. Okay. Thank you, Jay. Okay. And I'm saying, like, really, I'll try to put it one more level more specifically. Like, and again, I'm not saying anything about consciousness. Clearly, I'm totally losing my own consciousness. I'm saying about information transmission. I'm saying that object number 1 is apparently initiating an activity, an action that supposedly is determined by information describing object number 2. But object number two is not connected to object number one. Object number two is like somewhere else in empty space. And every time object number two changes its whereabouts or its size for that matter, object number one evidently responds with a new magnitude of force on a strict, like physical level. That has to mean that there's some way in which object number one receives or ever has access to the information that describes object number two. If I already think that that's a very strange idea, Newton thought that was a strange idea. But if you don't think that's strange, I'll go just one step farther and then I'll stop yelling and everything. To be more specific, if you believe, as apparently this equation would have us believe, if you believe that the information, like the size of the second charge and the address, the location of the second charge, if you are with me, that somehow that information, the Q and the R, have to be known by the other Q, like no, accessible to it, somehow being processed, used by it. If you believe that, and if you believe that new updates to that information, changes to that information somehow get transmitted from Q2 to Q1, then you might want to ask yourself, does that transmission of information take time? Like literally, does the information, I mean, when I'm talking about it as though information describing Q2 has to travel from Q2 to Q1 in order for Q1 to respond in a mathematically exact way. Well, is it actually traveling? I mean, is this a metaphor? Is the information actually traveling from Q2 to Q1 in the normal manner of travel, i.e. at a finite, well, I'll write it. I mean, what I'm asking is this. The question is, does this information regarding Q1 take time to travel to Q2? Like, I mean, that's like a super concrete question, I think. I mean, it's a super, I mean, I don't think the words are hard, but like, I think the idea is very hard. I mean, I'm obviously, and I see it's 6:30. I obviously have to, I don't want to just spend 2 hours just giving you hypothetical questions, but for the, just so that you know, really it was this question, like, does it take time or not? This is really what gave Newton a headache, because it really is a headache. And I'm not trying to give you a headache. I'm trying to just like actually, get inside of actual science with you to the extent that I'm capable. Like, again, really, I'm not trying to give you a headache, but I'm trying to show you that there's a real question behind these equations. Each one of these equations purports to answer a set of questions, but it just generates its own questions, right? And the question and I'm not going to take back these equations. I'm not trying to trick you. And, and on your final exam, you'll have to do like somewhat straightforward problems with these equations where you won't have to, like, for the most part, you won't have to like have another headache. But but let's respect these equations. Like the equations are true. They say that one object affects another object through empty space in a manner that is determined by the nature and the location of each of those objects. That means that objects share their information with other objects through empty space. Like, no matter what, if you accept GMM over R squared, or if you accept KQQ over R squared, what we're saying is that every bit of charge and every bit of mass that's in space somehow is communicating its existence, its size, and its location to every other bit of mass and charge in empty space. That is quite a bold claim to make about the universe. And if we're going to make that claim, one question it raises is, how does the information of one thing over here get to a thing over there? First and foremost, does it actually travel at, and if so, at a finite speed? Here's the deal. I will tell you. For new, like, okay, but I don't want to go crazy again, and I don't want to get off on a whole thing. But honestly, if you think hard enough about either alternative is weird. If the information gets there in no time at all, if the information is transmitted at an infinite speed, that's really weird, because then that means that distance doesn't matter at all. I'm not, you may or may not see what I'm about to say, and if you don't, it's fine. But like, if the sun pulls on the earth, if the sun sends the information of how big the sun is and where it is to the earth in no time at all, that means it doesn't take any less time for the sun's information to get to Earth than it does for the sun's information to get to Pluto, right? I mean, if it's no time at all, then it's no time regardless of where you are. So if that's true, that means all information gets everywhere at all time. I mean, it means the whole universe is capable of communicating with itself instantaneously all the time. So in some sense, and I'm not saying that's wrong. In fact, actually, that's what Newton thought to his grave. But it's not the way we think of things these days. That is too disturbing for modern physicists to consider. That to a contemporary physicist post Newton, we think that the information of how big the sun is and where the sun is travels to the earth at a finite speed and in a finite amount of time. And it takes less time for information to get from the sun to the earth than it does for information to get from the sun to Pluto, for example. And similarly with protons and electrons. The way we address this question of how does information get from one object to another through empty space is the way we say these days is we say that within that space between, and this is the subject of today, I mean, this is where this is all heading. The way we resolve this since like the mid 19th century, the mid 1800s, well, hello. Okay. Newton said, sun's over here, Earth's over there, or protons over here, electrons over there. I don't know how this happens, but somehow the proton tells the electron where it is and how big it is and how far away it is. The electron finds out immediately. I don't get how this is happening in empty space, but it's happening, and it's happening instantaneously, according to Newton. And Newton didn't like it at all, but he didn't have any better answer for it, and he drove himself sort of crazy with it, and he died. I mean, he didn't die because of that, but I mean, he eventually died. About 100 years later, we developed a different way of thinking about it. We developed a way of addressing this whole issue. I'm not saying fully resolving it. I'm not saying fully making sense out of it, but the way that, since a number of physicists known as or mathematicians and physicists and chemists known as Gauss, Faraday, Ampere, and Maxwell, all who worked in the first quarter, the second quarter, and the third quarter of the 19th century, of the 1800s, what these guys, what their work together says is, okay, here's a way to look at it. Here's a way to look at it. Like, apparently something is going on where things pull and push each other through empty space. From here on in, we're going to say that there is a kind of medium, a kind of medium, a kind of information carrier or information container or information arena that exists, that inhabits empty space, that exists in the space between objects. The space that looks empty between objects is not actually empty. There's something within, even seemingly, even in the vacuum of outer space, there is something between all objects that holds the information of all of these objects and allows the information to be transmitted back and forth and updated and communicated throughout all of space. The kind of medium that we believe in, or at least we picture and represent and use to make our calculations and make our predictions, which seem to work, the kind of medium that we now believe exists and inhabits space between objects is called okay, and I am watching the clock, and I know this is a lot, and maybe because I've been talking like nonstop without a break. Maybe we'll, if I can get this out, maybe we'll just leave a little early since you didn't get a break or anything. Maybe, hopefully. I should never say that. And I should never say that I'm not going to talk for 2.5 hours. But anyway, here's the key word. Where all of this, I know it sounds like I'm just like, yeah, well, I am just yammering, but it may sound like I'm just throwing out a bunch of like philosophical, like rhetorical questions, but they're not. The questions that I'm throwing out are actually meant to be the questions to which field is the answer. Okay. What a field is the punchline of all of this. Newton did not know about fields or use fields, or fields were not part of Newton's work. Fields were part of the work of physicists like about 100 years later. And from then on, I mean, they're still the work of physicists today. A field is a very abstract idea. It's a very unthingy idea. The field, well, and tell me if you want me to go back. I'm going to give you the math of a field first, because in some ways, the math is the most concrete thing to say. But wait, sorry, erase that. Don't write that. 1 second. I mean, you will write in a minute, but just hang on. Sorry. Oh, okay. Here's the math. In some ways, the math is a breath of fresh air. In some ways, the math is far simpler in some ways than anything I've said conceptually. So let me focus on the math for a second to try to bring this in. A force is something I do to you, always. I mean, a force is always an interaction between two objects. I pull you or I push you. Always, no matter what kind of force it is. But certain kind of forces, the fundamental forces, the gravitational force, the electrostatic force, they seem to happen through empty space. So they present all these weird problems that I've been like yelling about for the last 2 hours. So when it comes to fundamental forces, such as the electrostatic force, we change our thinking. We reconfigure our thinking so that when it comes to a proton and electron, once upon a time, we would have said the proton pulls the electron. But now instead, what we say is the proton creates a field everywhere in space. Even if the proton is the only object in the world, even if the proton is the one object in the lab, the minute you put a proton down, even though there's no other object for it to pull or push on, even though there's no second object to allow there to be a force, the minute we put the proton down, we say it creates a field. A field is, in effect, a force waiting to happen. The field, which exists everywhere in space, is like a function. It is a function. The input of that function is location in space. The output of that function is force per charge. So what I mean is this. We would now, instead of saying the proton pulls on the electron, we would say the proton creates a field. If the electron is the proton creates a field everywhere in space. If an electron comes along and lands in some point in space, then the field that's already at that point in space will pull on the electron. So we use to say proton exerts force on electron. Now we say proton creates field, field exerts force on electron. The field is the medium, like the third party kind of like we were talking about with waves and well, very much like we were talking about with waves and all of that. It's a third party. It's not a thingy thing. We're going to get into that. What it is a repository of information, or what it is our mental representation of information. Let me be more specific. Just looking at the time. So like so here's a vector. This is a vector diagram, the vector field diagram, or the vector field diagram due to a positive point source. So you have this positive point source plus Q, like a proton sitting somewhere in the lab or sitting somewhere in outer space. And the idea is I've drawn a bunch of representative vectors, just enough vectors to show you the pattern of what's going on. What is going on is this. If I were to pick any location, if I were to look at some location like right here, point P, at that P, there is a vector sitting there, a vector that's pointing away from Q, and that's pretty small. That vector that's sitting there represents the idea that if a 1 coulomb, a unit charge, if 1 coulomb of positive test charge were located at that place P, it would be pushed up and to the right. It would be pushed along the direction of that little arrow. It would be pushed by plus Q, right? In other words, if a little Q2, a lowercase Q2 of 1 coulomb of charge were hypothetically to find itself at that location P, then it would be pushed up and to the right. Why? Because there's a big positive Q like down and to the left from it. So it would be repelled. It would be pushed up and to the right, and it would be pushed up and to the right in the direction of that arrow that's pointing along a radial line connecting the two dots. But it would be pushed like by this small arrow. Why is it a small arrow? To show that it'd be pushed less than if it were over here closer in. Like, in other words, any point you pick in space, there's an arrow pointing in the direction of the force that would be exerted on you if you found yourself there, if you were charged. And the length of the arrow represents the magnitude of that force. The magnitudes are getting lesser and lesser as we get farther and farther away from the original charge. This is a bunch of vectors so the idea is the idea is that the minute positive Q1, the source, is placed anywhere in space, all these arrows spread out in space. All these arrows spread out in space at every point in space you can imagine. There's an arrow. Each arrow So each arrow at each point in space tells you how hard and in what direction +1 coulomb of hypothetical test charge. Each arrow tells you how hard and in what direction a 1 coulomb of positive test charge would be pushed or pulled if it were found at that location. I keep saying test charge and if and hypothetical and all that, because what I'm trying to say is, yes, once you put a charge at that location, then all these arrows represent force. Force is what the big capital Q1 would do to the lowercase q2. But the point of the field is that the arrows are there even before the second charge comes along to experience them. Let me back up again, and we probably will go moment soon. I know I'm saying a lot in a way. I'm trying to say that one way to picture the field due to a point charge is to picture a bunch of arrows that are radiating everywhere out in space. By the way, if you wanted to picture the field due to a negative, it would be the exact same thing, but a negative, all the arrows would point in. Because the whole idea of the field is the force that would happen if a positive 1 coulomb of charge were placed at a given location. The field is a set of vectors. The input for that set is location. The output is the vector. The vector is the force that would be exerted on a positive 1 coulomb of charge if placed at that location. So if the source is positive, it pushes on positives. If the source is negative, it pulls on positives. We're always, whenever we think about the field, we're thinking about what would happen to a positive recipient of the force. The point of the field is it's the information that's there, it's all the information that's there, ready to go, all the information that determines the force before the second charge even comes along to experience it as a force. So force is something that I do to you. Field is something that I do to a location in space, particularly to every location in space. A field is a bunch of arrows, bunch of vectors that represent forces waiting to happen. And let me pause again and say, I'm not actually asking you to believe that there are literally arrows sitting everywhere in space. Of course not. I mean, I'm not saying there's literal arrows in space. What I am saying, though, is that apparently there's information in space. What I am saying is that if there's a proton over here, then somehow there is, over in this point of space, the data of that proton, like the size of it, like the 1.60 times 10 to the negative 19th coulombs, and the location of it, such that if you put an electron over here, somehow it gets that information of that there's a proton over there, and the electron starts getting pulled toward it. What I'm saying is we picture now, from now on, that every time we put something in space, the information describing it, its size and its location, goes everywhere in space. And the best way we have for picturing this information, we picture it as arrows. As we picture it other ways too, which you'll learn next week. But we picture it, each point in space, as having a little arrow there, because the arrow represents magnitude and direction of force waiting to happen. We're not literally saying that there's literal arrows there, but we are saying there's literally information, and the package of information is most easily imagined and calculated in our minds as arrows, as vectors. So let me summarize this again, and then I'm saying force, electrostatic force, is KQ1 times Q2 divided by R squared. That's force. Field is KQ divided by R squared. Mathematically, field is just force per charge. Mathematically, field is all the information of the force divided by the second charge. It's all the information of the force waiting to happen. If force is measured in newtons, it's how many newtons I would exert, a big amount of coulombs would exert on you, a small amount of coulombs. Then field is all the amount of force I would exert on space. If you want to know how much force, so field is how much force I would exert on each and every 1 coulomb of charge that could be at a location. If the field at this location is 10 newtons per coulomb, that means if you put 1 coulomb there, it'll experience 10 newtons of force. If you put 2 coulombs there, it'll experience 20 coulombs of force. Field is force per charge due to some source that's sitting in space. That and mathematically it's easy. Not easy, but mathematically, field is just force per charge. Conceptually, field is the medium that contains the information. Field is the medium that allows one point in space to have access to the information describing any other point in space. If that seems like a weird idea, then the purpose of the first 2 hours of the core of today were to show you that that weird idea is not out of nowhere. That weird idea is our most effective, most successful representational answer to a question that is far weirder than it. The field is weird, but if we didn't believe in the field, we'd believe in something even weirder. The weird thing that a field is meant to address is that somehow stuff in space seems to numerically affect other stuff in empty space. That is so weird that the way that our best way of talking about it and making accurate predictions is to believe or model or posit or model that there's something inhabiting empty space called a field. We don't literally believe it's rubber or plastic. We don't believe it's made of materials. We believe it's information. And you don't have to believe in the word field. Just understand whenever we say the word field that we're saying somehow there's information in space, even when there's no matter there. The information of matter interposes between all bits of matter. That's what we're saying. Okay, that's a lot. I know I didn't give you a break or anything in the class. It does technically end at 7:10, right? Right. So if you're, and I will get, the exams will keep coming back. I apologize again about the exams, but I'm good if you're good. I'll pause if there's any questions. Like I'll stay if anybody wants to ask anything, but I'm good for you to go if you're good. So thank you for being so patient. I mean, are there any, well, yeah, are there any, well, if there are any questions, you can just stay and ask. I won't keep everybody else. But so have a nice night.
Thank you. Have a good night.
Thank you. Thank you. Now the class, you just said that. Okay. All right. Thank you. Thank you guys. Thank you for participating so much. Thank you. All right, I'll turn off the